This one?
Yeah.
Does that work? Oops, sorry. Wow, that went fast. Just a little bit at the beginning. All right, so good morning. I'm here to give you a bit of an overview of what we've been up to on the HiCAT team and how that maps to coronagraphic demonstrations for Habitable Worlds Observatory. So on the first day, Marshall did a raise your hand if you worked on the web, so we're going to do the same thing. Raise your hand if you worked on HiCAT. That's a lot of people, and I'm very pleased to be here to present on behalf of everyone. I counted 24 people just on the conference. Okay, so what HiCAT is a testbed in air. We have multiple chronograph modes that are available to us: classical EO, APLCs, PAPLCs, 2 different mobile mirrors. And the specificity of HiCAT is we try to run very fast loops to beat the environment constraints and demonstrate as realistic as possible multiple loop control, in particular EFC and low order control. So this is what it looks like. It's a big box in air. If you open it, there's a lot of optics. We have the appetizer here, 2 Boston deformable mirrors, and we have a segmented mirror as our telescope simulator. So here are some results in 3% bandpass. Those were obtained from our SAT programs. The important thing to notice here is that this is actually real time. This is how fast we're running the test bed. There's 5 iterations per second. And you've seen some other dark zone movies like this, in particular the Roman one. The movie looks the same, but it's completely different constraints. So first, that was their first time they did a dark zone during TVAC, so it was an incredible achievement. But it's a completely different set of parameter space with flight hardware, flight processes. And here with HiCAT, the key is that we can run very fast, very simple, so we can do a lot of experiments that are completely different parameter space. So we're getting 2 10⁻⁸ broadband here. Narrowband, sorry. So it is the contrast convergence. Now in broadband, it's a little bit different because we have to scan through 3 wavelengths to analyze our electric field. This is also real time. It's much slower because our exposure times are slower, and we need to do 3 exposures each time for each iterations. We're running down to about 6 10⁻⁸ contrast in this case. And this is a final image in true broadband. So this is no longer scanning, but holding the dark zone and then opening the bandpass fully. So similar to what CGI is doing when they're looking at their science target. There's been some questions sometimes on why we're still having the same contrast levels as when we presented this as SPIE a year and a half ago. Well, the reason is simple. We haven't tried to get better because we haven't had any funding to do so. So, so for now, that's what we have in terms of contrast results. So a little shootout to Emil's poor PAPLC, which were among the best and probably the best on HiCAT. Very good for small inner working angle, 2 lambda over d here. And 4 10⁻⁸ at very short separation. At the shortest separation here in monochromatic, we see that we're limited by the environment. Turbulence, vibrations can be improved to some level, but at some point, and this is why vacuum experiments are needed. So I'm going to show now the other part of HiCAT was not just chasing contrast number, but also demonstrating contrast stabilization under natural and artificial drifts because we have a real telescope simulator. So this is work that Raphaël Porcello has done. Here in this case, we can't scan anymore through the wavelengths, so we do a single band, so 6% band at once. And we are exploring different control loops. So first, we start by digging the dark zone. Each of these panels are about a minute of operations. Here we're in open loop. You can see some second panel, some fluctuations from the instabilities. Iris turbulence in purple. We're introducing small random walk drifts in piston tip tilt and degrading the contrast by about a factor 10 through this slope here. And when we turn on our low order wavefront control, you can't recover the contrast because these modes from each of the segments piston tip tilts are not seen by that sensor, but you can see that you stabilize this. It's more horizontal. When you turn the FC back loop, and now it's 2 loops running together, you are now stabilizing again. So by the way, this one with just the low first is stabilizing. That's the mode that Roman CGI is operating on when it's on science target. It maintains the EFC open loop, and it's closing the loop on the low order wavefront sensor. Here we're doing nasty things on the segmented mirror just to demonstrate that we can do that. Then we have another kind of turbulence that we can add, which is just low order on our continuous DM. So these are just low order Zernikeys. Again, here in this case, we degrade the contrast by a factor 10. And when we turn on the low order wavefront testing, in this case, because they are low order modes, we can actually recover the contrast back to less than 6 10 minus 8. And finally, if we do both loops, then we can get a little bit better, and that shows that the environment is being stabilized by the low-fuss. We get a little bit better. The EFC works a little bit better when the low-fuss is running at the same time. And then we do everything at the same time, which is the nastiest thing we do. We do a random walk drift on the piston tip tilts, and we're adding these low-order drifts on top of that, and running the 2 loops at the same time, and recovering the contrast below 6 10 minus 8. Okay, so if we pause for a second and think about the state of the art of what we have as telescope simulators for Hab Worlds, well, it's great we can do these experiments, but it's also limited in some sense. On HiCat, we have the only testbed that has truly segmented and active segments, but it's a very unrealistic telescope simulator. We have MEMS device, 1 millimeter segments. They have not, this is a company that went out of business 10 years ago. And other testbeds, I've used these chicken wire masks that are great to demonstrate the geometry and the diffraction, but they are not able to show actual segments and phasiness. So one of the advantages that we have on HiCat with this is because we know the starting wavefront map is very important when you start digging your dark zone. And we can simulate that. We can have actual segment piston tip tests before. With our mid-order wavefront sensor, you use a Zernike sensor. We can sense these piston tip tilts and then correct them before we start doing the dark zone. So we're demonstrating an operation scenario that's more realistic in that sense. By the way, that's exactly the kind of things that MAISA is doing on Keck. For those who saw our presentation yesterday, same kind of sensor and same kind of controls here. So what we'd like to do longer term is something like this, is moving away from these MEMS unrealistic flat segments, but building a telescope simulator that's starting to be a little bit more realistic, and not something that would be representative of the telescope in flight, just a ground equipment to simulate the telescope as the feed to our testbeds. So for that, we've been working on a roadmap. So HiCat has been completed now with this DM. We've done a first experiment in Satchel. I'm going to show some results. And that was completed last year. And at the moment, we're working on these 2 experiments. One is a closed-loop Zernike demonstration, and one is a first prototype of a complete Gregorian-style telescope that could be attached to something like HiCat. Longer term, the vision is something we call HOST, which is represented here. So think about something like the HiCat chronograph instrument, assist telescope simulator, attach the 2, stick that into a big vacuum chamber. That's what we're talking about, but it's very uncertain in the long term. Beyond that, there will be probably some need, but that's even more uncertain, something more realistic, maybe similar to what Ball Aerospace did for James Webb about 20 years ago. But here we're only focusing on these first steps here. So here's the first result from last year with this Satchel experiment. It's a very small vacuum tank, static, open loop experiment. We have custom electronics that are capable of picometer resolution in theory. We haven't tested that at this level yet. But we have managed to phase our little telescope in vacuum at about 10 nanometer surface error. And then we are working with colleagues on structural thermal modeling to improve the structure. So last night, Brian, you were asking me what keeps me up at night. So it's not contrast or stability, but the shenanigans that our gremlins are doing in the lab at night. So here's this little guy that we found messing up in the morning, our experiment. So for those who remember the web picture, this was just what we do at night. All right, so here's what we call capsules, the same little telescope simulator here. Now it's going to be in this vacuum chamber that was donated to us by Goddard. It was very conveniently the right size for what we needed. We've been aligning it here. You can see the 7 segment here. These segments are flat, so it's still kind of like HiCat in terms of the modes you can simulate, but at least it's more realistic than it's the first step to demonstrate something even more realistic. So here are our first results. We're in the process of phasing this little telescope. Here you see the fringes on our Zernike sensor as we move some tilt on one of the segments with our piezo actuators. This is the Zernike sensor on its null. We're tapping a bit at some moments on the table so you can see vibration that it actually is real. And this is the light diffracted halo beyond the pupil by the Zernike sensor. So we're still in progress of the alignment from a not really stacked image to partially stacked to the beginning of a single coherent peak of about lambda over d in diameter, so it's pretty exciting. We'll have to phase that in broadband, so there's still quite a bit of work to do. And our vacuum tank is ready, so for now we're doing the work in air, and we'll plan to transfer that in vacuum hopefully relatively soon. So thinking longer term with host in mind, I just want to say a few words about our thoughts on contrast and stability timescales. So the particularity of HiCat is that we go very fast. We're running at several hertz, but for now we're at 10⁻⁸ in air, and eventually we need to get to Habitable Worlds in flight at 10⁻⁻10 contrast, where the stability is of the order of picometer. But stability in itself doesn't mean anything. We hear about picometer. What is really important is picometer over what timescales. And the timescales that relatively matters here is the timescale of the wavefront sensor. And that's the advantage we have on HiCat in air because we run very fast. So going through 3 orders of magnitude of timescale and 2 orders of magnitude of contrast seems not the direct path to us. And what we think is the right approach is to attack the contrast first at rapid timescale. So you still have to worry about picometer, but over 10 milliseconds, it's easier than running about picometers of tens or hundreds of seconds, and then grow the stability over the timescales in a second step. So just my conclusions now. HiCat is the only test bed that so far has reached 10⁻⁸ with a truly segmented aperture. I put an asterisk here because there's actually a new test bed that has its first flight. There's a poster by Charles Salard and Patrice Martinez. They're from the University of Nice, and they have this test bed. It's an infrared test bed for ELT, and they've reached 5⁻⁵ dark zone now with a truly segmented aperture. It's also an IRSAO mirror as well. HiCat has completed 10 years of development. I wanted to put all of the, try to put all of the logos of all the benefactors that we have. We have a lot of in-kind contributions of various kind. We've been supported about 20% of the, I was calculating, are from external sources, and especially from France, and the rest has been supported by NASA and STScI funds. We haven't been able to make much progress on the HiCat test bed because it's because of funding, and we've been stopped for a year. So contrast is not physics limited, but it's programmatically limited at this time. We've been running on fumes and friendship with all of our partners. Hopefully we can get back on HiCat dark zone soon. Fortunately, ASSIST is going forward, and we've made some progress with our telescope simulator. Thank you.
Hi, thanks, Remi, for that talk. Do I understand correctly, your 6 times 10 to the minus 8 current contrast demonstrated, is that in a half dark hole or a full dark hole?
No, that was the full dark hole.
That was the full?
Yeah.
Okay, so let me ask about that number, which is that that's in air, and with your segmented test setup. The other coronagraph experiments in air seem to get about 10 to the minus 8 contrast, so about, as I understand it, like Dimitri's, or when Gareth sets up an experiment in air before moving it into vacuum. Okay. So is that factor of 6 difference between what you get and what those other folks get in air, where does that come from? Is that because there's some lab setup issue for you guys? Is that coming from the segmented nature of your demonstration itself? What's limiting you guys besides programmatics?
All right, so there are a couple of things. So 6 10⁻⁸ is broadband. I'm not sure, if they're, you have to see also what band they have. The second thing is HiCat is a very complex instrument compared to other testbed because we can have it both ways. We want to be as system-like as possible, but that means we have 5 pupil planes to align. That's a lot of things that can go wrong. It's much slower to do that. The other aspect is we had all of this work was done on the SAT, and you're very familiar with this because the milestones were developed in collaboration with EXEP. And the milestone goal was to have 10-7 contrast. So we reached 6 × -8. We had all of our other things to demonstrate, like this cartoon movie of stability. So we actually actively stopped trying to improve contrast, and then we ran out of support, so we never tried. So at this time, there's plenty of things that we have a long list like this of things that we want to improve. It's true that we have this contrast of 6 × 10⁻⁸ in broadband, and actually I think there's some interesting things because I was looking in the literature. There's some other test beds that have very similar numbers. In particular, the Arizona test bed is a recent paper. They have the same number, but a factor of 10 lower. 1 × 10⁻⁸ in narrowband, about 2 in monochromatic narrowband, and about 5 or 6 in broadband. So I think this is something that not just us are faced. We still have some reconciliation, and the DST also, I think, between what we can do monochromatically and what we can do in broadband. But mostly it's been limited by support at this time.
All right, I think we're going to have to move on. Thank you so much, Remi. Microphone. Yes.